guys, so we're going to do DNA replication today. I want to go over a couple of important parts. Some people were having trouble with leading a strand versus lagging a strand and what that entailed. So I'm just going to kind of go through all of the pieces and parts that are included on your replication model, the things that you need to include. So we're going to talk about that, okay? So first I wanted to talk about DNA structure, okay? You know that there are base pairing rules, and the base pairing rules are A binds with T, G binds with C, always. If you have a C on one side, you have a G on the other side. They always bind together. C and G bind together with 3 hydrogen bonds, and A and T bind together with 2 hydrogen bonds. And those hydrogen bonds bring the 2 strands together and provide stability for the DNA. So you have a backbone, which is a sugar and a phosphate, okay? And it kind of goes like this: sugar, phosphate, sugar, phosphate. That's what we call the sugar phosphate backbone. And then you have the nucleotides here. And then the nucleotides come together with however many hydrogen bonds with another strand that is, instead of being, this is the phosphate, okay? That means this is gonna be the sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate. So basically you have one go in this direction and one go in this direction in terms of the order of the sugars and the phosphates, okay? That's what we mean by anti-parallel. If this one starts up here with the phosphate, this one's gonna end with a phosphate. And the way you can remember that is that 5' has the phosphate, okay? 3' has the sugar, or more specifically the OH group on the last sugar sticking out, okay? So 5 phosphate, 3' is the sugar. So that's what we mean by anti-parallel, is that they're still parallel, but they're just flipped, okay? Hydrogen bonds, 2 versus 3, we just talked about that the G and the C have 3 hydrogen bonds and the A and T have 2. Yeah, that's pretty much it for the first part. Okay, so now we got this guy. This is a DNA strand that is in the process of replicating. And what we have here, this whole big thing, this is called the origin of replication. Okay, origin of replication, sometimes it's called the replication bubble. Okay, so it's this big area where the alpha helix is opened up and exposed, the nucleotides are exposed and not connected together. So that's the origin of replication, or the replication bubble. And since your DNA is so big and extensive, one piece of DNA can have many, many replication bubbles on it to make the process of replication faster, right? It's obviously having one start at one end and go all the way to the end is going to take a lot longer than if you have multiple replication sites on the same strand, okay? So you can have multiple of these bubbles. So DNA starts as an alpha helix, and there's a couple things that have to happen even before new base pairs can start being added on, okay? And the first thing is an enzyme called topoisomerase, okay? Notice it's an ASE, that's because it's an enzyme, and that's it basically taking the torsion out of the alpha helix, so it's untwisting it. Then after you have that part happening, then we have something here called helicase. Again, ASE, another enzyme, another protein. So this helicase then is basically busting up the hydrogen bond. So if you have your nucleotides and you have your hydrogen bonds, helicase's job then is to basically get rid of those hydrogen bonds and unzip the DNA from each other. So basically now we have just the sugar phosphate backbone and the single nucleotides, and the same thing over here, the matching strand is on this side. Now that can make it a little bit unstable. So we have even more proteins here, and these are called single strand binding proteins. Okay, and they're going to be here as well. And those are going to kind of just sit there and make sure that nothing happens to the code, right? Because this code is all important. The code is basically the instructions for how everything that the organism needs, from proteins to what makes it, what color, everything about it is in the genetic code, so it has to be conserved. So these are pretty important to keep things from breaking up, from losing a nucleotide, from adding a nucleotide. So keep the genetic code exactly as it is. Okay, so that's their job. Now, it's important to get an idea of which direction replication is happening in. And when you have a bubble like this, DNA replication is happening in two places. Sometimes it looks like it's going in this direction, but it's not. You're basically starting here at the origin of replication, and it's being copied in this direction, and it's being copied in this direction. So it's bi-directional. So it's actually starting here and going this way towards the helix. So these guys are the leading, they're starting the process. They are unwinding it. They are breaking the hydrogen bonds. So this goes first, and the bubble will kind of follow it, okay? So remember that, we're going in this direction. We're gonna kind of ignore the second half of this right now, and we're coming in this direction, okay? Now that's gonna be important here in a minute. So what has to happen for this whole process to start is we first need something called a primer. And the primer may be several nucleotides long, but the primer, I'm gonna put, is a small strand of RNA that is gonna help the process start. It will be removed later, but it's just priming the pump, if you will. It's just getting it started. And this is put here by something called DNA primase. Okay, another enzyme is putting the primer here. So we have DNA primase adding a DNA primer. Now the big guy can come. And the big guy is, this is DNA, DNA polymerase. DNA polymerase is, his job is going to be taking the nucleotides out of the cytoplasm and picking the right ones, because they gotta go in order, and putting them in order, okay? So for example, this is a, he's gonna have to put a T here. And this is a G, he has to find a C and put it there. This is a G, needs another C. So basically DNA polymerase is gonna sit here and start working in this direction, okay? Now, both of these strands happen a little bit differently. This side is gonna happen a little bit more easily. We're gonna say that this is the 3' end of that side of the DNA, and this is gonna be the 5' end. So if you follow this strand, this black strand, if that's the 3' end, that means this is the 5' end. If this is the 5' end of the blue strand, then this is the 3' end. Remember, they're anti-parallel, okay? Now, and by the way, you can't tell from this drawing which is the 3' end or the 5' end. When you see drawings like this, you're gonna have to rely on the labeling of it. So I'm just kind of making up the sides right now. But if you were to really identify it, remember that 5' end is going to have the phosphates. Okay, so here's where it gets a little tricky in terms of how things work. DNA polymerase will only build a strand of DNA from the 5' to the 3' end. So we're going to go 5' to 3'. Now, if this is the 3' end, okay, of this strand, we are building an anti-parallel one, which means that this is the 5' end of the new strand, right? Because if this is 3, this has got to be opposite. It's got to be the 5. So this strand, because we're moving in this direction, this strand is being built from 5' to 3'. Okay? Because remember, these are going to become 2 separate DNA strands shortly. And then that means that this one, if this is the 5' end of this strand, that means we're building one that is going to be 3' to 5'. Well, we already talked about how DNA polymerase really only likes to build it in the 5' to 3' direction, okay? So up here, we're going to call this one, because it's being built in this direction, 5' to 3', 5' to 3'. This is called the leading strand. Okay, it's the leading strand because it's going in the direction that DNA polymerase likes to build. It is building one in the 5' to 3' direction, so that makes it the leading strand. This one is going in the opposite direction of what DNA polymerase likes, so we call this the lagging strand. Okay, so what has to happen in this situation is that when the DNA polymerase, or I'm sorry, the DNA primase puts a primer, that part's going to stay the same. We're going to put a DNA primer on. DNA polymerase is going to bind. Okay. And they're going to add nucleotides, but it's going to add it from the 5' to 3' directions. It's going to go this way for a short distance. Then it's going to come a little further because this whole thing is moving in this direction. So we're going to put another primer a little farther down. DNA polymerase is going to move, and we're going to build this way, 5' to 3'. And then again, as this moves, another primer will get put down here. DNA polymerase will start adding nucleotides in the 5' to 3' direction. So this one is what we call continuous because it starts 5', 3' and just goes along, zooms down. This is discontinuous because it starts here, goes for a little bit, stops. Starts here, goes for a little bit, stop. Starts here, goes for a little bit, stops. So it's called discontinuous. Okay, and then you have these little fragments. And these fragments, these are called Okazaki fragments. Okay, and they're named after the Japanese scientist who's figured this part of the process out. And basically these little fragments are kind of right now not connected together. They're by themselves just floating there with these RNA primers in between them. So it takes another 2 molecules. You got to get a exonuclease. And this guy gets rid of the RNA primer, right? Because our DNA strand, we don't want RNA mixed in with our DNA strand. So it gets rid of those primers. And then you have, I'm running out of places to put things. Then behind it you have DNA nuclease. And the DNA nucleotides, or the DNA nuclease, sorry, they're basically going to put the Okazaki fragments together, okay? So they're making it so that, so these 2 things are kind of the cleanup crew. They come behind after the fragments are made, they come behind, get rid of the primer, and then bind those 2 fragments together, and they'll go all the way down the row. As this thing gets chugging in this direction, then these guys, the cleanup crew, are coming and putting the fragments together. So you can see that this lagging strand is a lot more, I don't want to say unelegant, but kinda, you know, it's kind of a lot of pieces and parts that have to get put together. It doesn't work as beautifully as this machinery up here does. This kind of just goes along perfect as can be and works really well, where this is just kind of like chugga, 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 you know, goes a little bit slower, and then there's all this cleanup that has to be taken into effect. This exonuclease, by the way, will also go to the beginning of the origin of replication for the leading strand and also get rid of this RNA primer. Okay, so we got lots of pieces and parts here. I just want to make sure I have touched on everything we need to talk about. Let me look at your replication model. Yeah, it looks like it. So hopefully, I mean, that kind of clears up a little bit the DNA replication. If you have any questions, let me know. We can kind of go over it. Obviously, this will be kept up in class, and you guys at home can watch this a couple of times if you miss something, or schedule a tutorial with me so that we can kind of talk about it. I would also suggest looking at YouTube. YouTube has a lot of DNA animations where they show this process animated, and sometimes that helps things click better from rather than looking at static images. If you look at like a video of this origin bubble moving down and seeing these things kind of happen in not real time, but happen in front of your eyes, it might be a little bit easier. So hope that helps, guys. Take care.